What's up, y'all? Right now, we're about to talk about a presentation called Power to the Students, Democratize Discovery in STEM Classes. My name is Jeff Anderson. I'm a full-time math instructor at Foothill College. I'm going to pass the mic over to my two co-presenters, starting with Hayden Seto. Take it away, Hayden.
Hi guys, my name is Hayden Seto. I'm an electrical engineering major at San Francisco State University, and I was a Foothill College student from 2016 to 2019.
And my name is Chris Sakurada. I'm also an electrical engineering student at San Francisco State, and I am also a Foothill College alumni. I attended Foothill from 2014 to 2019. Okay, so we're here to talk to you about our project, which involved creating the current and voltage sources that you see on your right. Independent current and voltage sources that you see on the right. And then we eventually produced or provided the electronics learning lab kits as a whole. But that was our game.
Yeah, and particularly, I can kind of get some context here. So I met Hayden and Chris, I think both of them actually in a Math 1C class. I think I met you, Hayden, during the summer. That was a 6-week class. And Chris, I think I had met you the spring beforehand, right?
Yes. Yep.
And when I met them, I was in the middle of a much larger project, which was to try to empower students to discover STEM by themselves. One of the things that I really appreciated about both of you guys was your willingness to like engage in stuff outside of the class. I remember one time during the summer, Hayden, you had asked me the question, do you have any projects? What was it? Do you remember that story?
Yeah, I think it was, I just finished your final, and your class had a huge impact on me and questioning how I learned and why I wanted to do this. So I reached out to you to see if you had any projects, and you asked me what my major was, and I said electrical engineering, and you're like, oh, I have the perfect project.
I have funny stories about that. Like the part of that was really interesting, which we'll talk about later, was I was looking at that moment, I was thinking about spending like 4 years teaching myself enough to be able to do this. And you came in right as I was like ramping up for that part. And so you were able to do stuff that would have taken me so much longer than you did. And particularly one of the things that I like to think about is Chris and Hayden, I like to call them my angel investors in this project to democratize math modeling. So in my classes, I talk a lot about the idea that mathematics classes actually are only a very, very small part of math education, particularly applied math education. In particular, I talk a lot about this concept of what I call the applied math modeling process, which has 4 stages. The top stage over on the left is called the real world problem. And I define in my classes a real world problem as any problem that can be measured using quantitative data, or any problem that matters to students. And in this process, this model goes something like, we start with a real world problem in our world. So for example, how do we fix climate change? How do we deal with income inequality? How do we deal with systemic racism? All of those are measurable using data. In the case that we're talking about how do we measure circuits and understand the behavior? And then we translate that into an ideal mathematical model. That process we do via mathematization. I would actually say that one of the reasons that we have science classes in STEM majors is because science classes teach us in this model what it means to turn the real world into math equations. So this center of mathematization, you could think about it as science classes. And then once we have the ideal mathematical model, then we can use what we call math classes or mathematical analysis to produce what we call an ideal solution to that. So it goes something that exists in the world of the students, use science classes to translate that into something that exists in the mind of a mathematician, use mathematical analysis to translate that into some ideal solution, and then use human thinking, critical thinking, to interpret what that means in the real world. Good applied math problems are really, really hard to solve good real world problems are hard to solve via like brute force, but can become much easier in mathematical analysis. Now, the problem is that in order to have students discover this for themselves, it is really expensive and difficult. it's actually not easy to have the students run through the entire thing, which is why most math classes don't even show you how the math is done. They just literally say like, here's the math. It's not my problem to teach you this. You got to figure out how to use it in your own life. One of the things that I contend in my classes, and before I met Chris and Hayden, I was actually working on this problem, which was how could I actually have students run through the entire process for themselves and discover that math is real and alive in their own lives without having to trust me. The thing I love to say to my students is, don't trust me, I'm full of malarkey. I don't use the word malarkey usually. In fact, test this for yourself and figure it out. And so what these guys did was take an idea that existed in my mind that Mike Sassnett helped to create the first version of, which was allow us at a very, very cheap cost, so as cheap as possible, allow us to empower students to experience a real world problem, and then run through the entire modeling process and get a meaningful solution using measurement, and compare that solution to the output of an ideal model using math analysis. Or another way to say this is to democratize mathematical modeling, to make it possible for students at Foothill Community College for bare minimum cost to see how math works in the world. And it's not just math either. We'll talk more about the idea that the project that these guys worked on came alive in engineering, physics, math, many STEM classes. And so before I met them, I was kind of figuring out how to do this whole manufacturing process. Hayden comes at the end of his final, asked me that question. The fact of the matter is, like, I had this project waiting, and these guys picked it up and made this dream of mine come into reality in so many important ways. This presentation that you're looking at is the story of that progress. And particularly, Hayden, maybe you want to talk about the sequence of steps and progression.
Yeah, so when we joined the project, Mike had already done some amazing work. He did the initial engineering. So he designed the two circuits, one for the voltage source and one for the current source. And you can see in version 0, he had it breadboarded. And then he got a fully working prototype packaged and everything ready to go. And this is kind of what we were handed both of these. And
Mike, just quick context. Mike is Mike Sassnett. He's a retired electrical engineer. He did really amazing work in lasers, a long career. He donates his time to Foothill College, and he gave us a gift, which was his literally intellectual work to produce these prototypes. And so that's what he was saying. That's what Hayden was just saying. Sorry, yeah. Hayden, take it away.
Got to shout out Mike. He was a great mentor, as well as Jeff, in this project. But we jumped in at right after version 1. And we went through a series of meetings to figure out how do we get these into the hands of students in a manner that is cost effective and robust, so that we could continue using them for many labs and relatively quickly. So this presentation focuses on version 2 and 3. There's actually more like 4 iterations of the circuits. And then where we are currently today is version 4, with Mike having picked the project back up and fully deploying them. And it's almost like he took them to market in a way.
Yeah, so we're about to tell the story of how Hayden and Chris took an idea and actually created a manufacturing process, as well as kind of the final design to put these into the hands of students, which is just freaking amazing, right? You're making my dream come true, guys, like a Disney movie almost.
So this is the start of the design process for us, and this is a picture of kind of what we received for each, the current and the voltage source. We received it like a drawing of a basic circuit. And so from receiving this, we went into the initial prototype stage. And that prototype stage was a series of meetings. We were deciding on the device requirements and the constraints of what we really wanted to achieve. And we decided that it should be as low cost as possible, as user friendly for students as possible, and as small as possible, so that students could really set these up and do these labs from anywhere. And so after our series of meetings, brainstorming ideas, we came up, or Jeff actually came up with the idea of having a current or voltage source as a sort of battery cap. And that's kind of what you see at the bottom of the screen here. At the bottom of that bottom version right there. That's kind of our initial idea that we decided to go forward with. And so the next step in this was really doing the research on our materials and the software that we were going to use to produce this, right? So we went and we tried to define like which were going to be the lowest cost components, what was in stock, and what type of electronic CAD software that we were going to ultimately use. Now, for this project, we decided that would be a software called Altium, and that required that we additionally hunt down schematic symbol and PCB footprint that you see up here in the upper right for each component that we were going to use. And so that was kind of like just collecting in a way our library of components and making sure that we had them in software and making sure that we had them in stock at the websites where we're going to be purchasing these. So once we had all of that kind of aligned, we went into a process called schematic capture that Hayden's going to talk about here.
So the schematic capture, just like what it sounds, we took the schematic that we had on paper and captured it or input it into our ECAD software. ECAD is electronic computer aided design. And it allows us to link all of those components that Chris mentioned earlier together and tie them from there into a basic board layout. And with that board layout, we were able to go into the prototyping phase. And we had access to a desktop CNC mill, which was really cool in that we could cut out a few of the boards, a few different iterations to figure out dimensionally, like if the components we picked would fit with the various connectors we were trying, what side the wires were going to come out, and also if the cap would actually work. And at this phase, we finalized that we were going to continue to go and aim to use a cap, or to get the circuit in the size of a cap. So then we moved back to Altium and did a formal board layout.
Yeah, just real quick, I wanted you to not all viewers might understand what a mill is, and I just kind of wanted you to describe in simple language what's happening in this photo, because I think this was really cool. I thought like when you all were doing this and bringing them in, I still have them over here, right? Like, so could you just what is a mill and what is this picture of, and
oh yeah, so a mill is
annotate it there.
I guess. So the mill, if you imagine like a router or a Dremel, it removes material, and it's CNC, so it's computer run. So you take your design files from your ECAD software and you upload it to a separate software that the mill has, and it will translate your board to this piece. This is actually a piece right here of fiberglass that's copper clad. And what the mill will do is it'll run and remove copper around the traces that you want for your circuit. And it's like, I think this board took us like 15 or 20 seconds. So it cuts it out really quick. So you see in the first picture, that's the simulated model of the mill cutting the board out. Then the board actually cut out.
Yeah, so so what you're saying is that the Dremel, basically it's like a sawtooth or like a little drill. This is over here, this is a computer graphic representation, and then you actually input that design. This is a real representation where the little drill like took out parts so that the copper pieces create connectivity, and then that allowed you to prototype the damn thing and realize that like the initial design phase that you had was something that was like worth pursuing, right?
Yeah.
And I just love, like, you all, I love that. I wanted to capture that because I think it's such a powerful lesson. And I actually learned a lot watching you all do this, like just the iterative process, and like before you sink into the larger thing, test it out, etc. So anyways, let's go back. We can go back to the other one. But I wanted to call that out because I thought that was really special, and you all worked hard on that.
That was a really fun process for both of us. So the board layout, we went back to Altium and we did a more formal board layout of taking in the considerations and decisions that we made from the milled assembly, and did this iteration here where we had the snap connector holes, and this ended up being, I think, 1 square inch, and then Altium lets you convert to a 3D step file. So along the way, as you're designing your board, you're placing the components on this board and routing them. You can see in a 3D model, what it's actually going to look like dimensionally, and make sure things are as you are imagining them in the 3D sense. And once we had finished that, we needed to find someone to manufacture these. And obviously one of the requirements for the project is for this to be as cheap as possible. And we were really lucky in finding a company called JLC PCB. And they are a circuit board manufacturer in China that does relatively low volume, like the same kind of maybe hobby and prototype level stuff that we were at this phase. And it was awesome in that I think we paid $20, $30 for 150 boards, and we got them in 6 or 7 days, which was very unexpected. So once we got the boards, our job was to build them. So Chris and I each took some home and worked on soldering all the components in, stripping all the wires, and mounting all of the connectors. And as you can see, there's like a pile, the white and black leads correspond to the current sources, and then there's a pile of the voltage sources there, finished and ready to be tested. We then went and tested them, and then we were on to packaging. And Chris can tell you about our ideas for how we wanted to package these.
So to package them, we decided to use what's called potting. And potting is basically a process that we use a plastic or some type of enclosure. We insert really the circuit or the object into the enclosure, and then we pour epoxy over it to seal it and really make it like a finished inaccessible product. So to do this, we met up. We had 75 of each, but we knew that epoxy would be setting. We had about an hour before. Once we mixed the two chemicals together to form the epoxy, we had about an hour till they was done, no matter what we set. So we set them all up on the table and went and decided, like, okay, we're gonna double Ziploc bag this, just kind of like how you frost a cake. We mixed this, we mixed it together, we poured it, and then it was like go. And so we're running across this table, and Hayden's holding the wires for each, making sure that it doesn't, and that it ends up as flat, and I'm like basically pumping epoxy into each of these boxes until we get it like about 3/4 full. We run through the whole table doing them all, and then we run back and they've settled, and we kind of like put the little topping on top of each one.
Smooth it out.
And so we kind of like did this like as quick, but we pretty much timed it.
It was a mad rush.
Yeah. But and so after that, we let them set overnight. And really what we end up with is a series of voltage and current source that you see on the next page. And so here you can see on the top, we've got a voltage source designated by a red and black wire, positive and negative. We added the sticker just to make it as user-friendly for the student as possible. And really the same thing happens with the current source, designated by a certain arrow white to black, and that is kind of like the common circuit schematic designation for voltage and current sources, to try and just make this as easy and real to use for future students. And then they were ready to be deployed. So it was ready to be added to these kits that would go into the future electronic lab kits, where we would hope.
Yeah, so I have two things to say on this. Number one, you guys, one of the things that I just was like really impressed with was you thought to put the stickers on without any guidance on that. Like, we were basically working on the design team, all three of us going back and forth. Mike would come in sometimes to kind of guide some of our thoughts, but we were just like, it was nonstop. Like, you guys were doing all the hard work and I was kind of sitting back drinking pina coladas or whatever. And then eventually I'd be like, what about this, right? And then I remember, like, you brought them that morning, right? Because you guys had been, I had a presentation at CMC Cubed, Council of Mathematics for California Community Colleges. I was basically launching this to the public for the first time. And I think both of you guys showed up with a box, right?
Mm-hmm.
And I just remember being stunned by the fact that, one, you did all of that without any pay. So I think I should be arrested for violating labor laws, right? And then two, that you had really thought outside of the box, so to speak, to think about the end users and try to decrease cognitive load. I was really impressed with that, thinking out of the box. And the cool thing was, the day I got these, it was probably like December 8th or something like that, that Friday, it was during finals, right?
Mm-hmm.
Which is just crazy. You were doing all this, like, yeah. So I got those the next morning. I go down to Monterey, and that was like a 24-hour night for me. Like, I don't think I slept more than like an hour in probably 36 hours of my life, because I was prepping the stuff. I was grading finals. We launched them to that public. There's a YouTube talk on that actually shows the entire launch. And then from that standpoint, I had one more quarter, and then I was off for 9 months, and I used your sources in independent study. And then I also made a bunch of YouTube videos to be able to share these with students. And I'm currently still using those. So the fact of the matter is, you guys turned an initial design into a product that was being used in the classes. And what was really cool about that was, at one point, I think we had this meeting with Mike Sassnet. And at the beginning, Mike was really, really generous with his time and energy. But I think he was excited to be able to pass this off to the next generation of engineers. And the two of you picked this up, designed a product, which I think we could actually sell. I have been really, really adamant that I want this to be low cost. And when Mike saw it, do you remember that day that we gave it to him and how his face lit up? I felt like we made him proud that day, I hope.
Yeah,
right?
I hope so too.
Yeah, because he was so kind to us. And I was really proud, because I like to say, like, you all were the angel investors in this project, and Mike was venture capital, and he really saw the potential, and the fact that you made this come to reality, I think, gave hopefully some inspiration and some support to the idea to like bring in the big gun, so to speak. So the next iteration of this, Mike Sassnet, who is the lead engineer, he developed the circuit, and he's really been a steward of this project. He connected with his friend called Jose Espina, and then the two of them worked to do a new iteration and contacted Sunnytech. And what that allowed us to do is, instead of Hayden and Chris in a room sweating with epoxy, they really automated the design process and created these next generation. And what's really amazing about this is that the moment we got this new iteration of those sources, we actually created a lab kit for 3 classes at Foothill. It was Math 2B, Engineering 11, Physics 4B, and Engineering 37. And we went through the process of ordering. We ordered 2,000 of these, spent a lot of money to make that happen. And then we've actually implemented this in, 7 different classes affecting 163 different students. So students were able to, during COVID, drive to the library, pick up these lab kits, which fit into a Ziploc bag, drive them home, and do all of their lab equipment on a kitchen table with no fear of dying, no special training, and for a cost that is actually affordable. Previous to this project, in order to get a voltage source, you had to have a bench power supply, which is somewhere between $50 and $500. I'm really proud that the cost per unit was, what was it, Chris? Like
$450. It was probably in between $4 and $450 was the ultimate.
Yeah, so Mike and Jose and Sunny Tech, I think their cost was like $6 per unit. So we actually underbid them, but you all gave like hundreds of hours of labor. Yeah, so yeah, you can see why labor laws are important, right? But the fact of the matter is, like, that's an order of magnitude saving. So instead of $50 or $500, it's only $5 per unit. And it allows students during COVID, this has been amazing because it means that instead of having to do virtual learning, you could do actual real world measurements, which wasn't possible before this. And the really cool thing about that is that, as the leader of the class, I've had the opportunity to have individual conversations with students, and I've seen some really major changes. I had one guy change his major from the dark side of CS to the Rebel Alliance called Applied Math, which was awesome. I had another student say that they used this experience during the internship interview, and they successfully landed that internship based on this whole idea. And I've had many, many students communicate to me personally, which we're going to capture in some interviews, just how impactful this has been. And from that standpoint, I just, I have to bow down to Mike Sassnet first and foremost for really providing the initial design. But I have to say that you guys made this happen. You designed as students an experience that empowers other students to make learning come alive. And I think maybe Hayden, you wanted to talk a little bit about that in the sense that, and Chris, being able to see these real world problems in action is so different than just trusting some authority figure about, yeah, just trust us, kid, this is going to work.
Yeah, I think you spend so much time, we'll use the example of, I guess, circuits class. You spend so much time working on the theory and trusting like Ohm's law and KVL, Kirchhoff's laws, and you use them in your written tests, and then you get maybe 3 hours once a week in lab to go try and prove it to yourself. But you're also competing with multiple lab partners for time, and I think that with these P-block kits, you have the ability to do it on your own terms. So like, it's cool that, like you said, you could be at your kitchen counter doing your lab or verifying something for yourself, or you don't even need electricity. And in that sense, all the theoretical work that you do is now you have a place to store it by proving like with a applied experience like this, it's easier to organize that information and I think use it and have a better understanding of it long term.
Yeah. So with that, that's kind of this part of the presentation. We're going to have a upcoming much shorter presentation in the Foothill College Research and Service Learning Symposium on May 20th, and we'll kind of overview this. And I'll also have a support website, but I just want to thank both of you for your contributions and to put it on the record that this was the early stages of this were kind of a community-based design process led by a master engineer and 2 Foothill students. So thank you both.
Well, thank you. Thank you and Mike. It's been a great experience. It's been some of the pieces that we put together of where we were at the time and what it really allowed to us to see the importance of like having an applied learning experience like this. So thank you.
We really appreciated the opportunity. Thank you.
You make dream comes true. I feel like we need a motto, and then I want $100,000 on both of you guys. Cash, right?
That's what you're giving all of us. Thank you. Thank you, Jeff.